Okay, good morning everybody. I'm Surya and Dasika and I'm doing my Masters under Dr. Saket. Today I'll be talking about my Master's project, which is assisting the spatial accuracy and precision of LiDAR and Photogrammetry for remote sensing in agriculture. And my company members are Dr. Gorak, Dr. Sama and Dr. Walcott. So a brief intro about me. I come from southeastern part of India, from Andhra Pradesh. It's about right here, it's about 100 miles from the coast. I did all my schooling right there, and all my family is also around the same area. And for my undergrad, I went to Indian Institute of Technology, Kharagpur, where I did my bachelor's in technology in agriculture and food engineering. It's about right here. It's about 800 miles, I would say. And that's about me. And I don't have any brothers and sisters, so. This is the presentation outline I will be talking about. First, I will be talking about the introduction of remote sensing, just a brief intro about remote sensing and the techniques I will be using, and also the motivation behind the project. And after that, I will be talking about the objectives one by one and what I accomplished up to right now. So the low altitude remote sensing in agriculture, it's commonly known as unmanned aerial systems (UAS). It's basically integrating different sensors to unmanned aerial systems to remotely estimate plant and soil physical and biological parameters. And for my project, it's plant physical parameters like leaf area index, plant height, plant biomass. And they are really important because they are really good indicator of health and yield potential in crops. You can compute fertilizer requirements. You can also model different processes like photosynthesis and evapotranspiration. But most of the traditional remote sensing methods are really time and it will require lots of time and labor. But if you use unmanned aerial systems, it will require a lot less time. It's more like time, labor, and cost effective. But before UAS, there is satellite imagery which is existing for a long time. But there is a rapid advancement of drones in agriculture because it's mostly due to drones have more temporal and spatial resolution. You can really see up to 1/100th of a meter by the drones, which you cannot see by satellite imagery. You can see each plant's leaf area index, each leaf height, each leaf area, everything. And the techniques I'll be using is LiDAR photogrammetry, and there are some few techniques. As you can see in the picture, this is a spectral NDVI imaging of Donaldsonville farm in Louisiana state. So as you can see, you cannot predict the crop physical parameters through this image. So we want to use other techniques like LiDAR and photogrammetry, which are the most rapidly advancing techniques right now. So I'll give you a brief technology before going into some introduction. Digital elevation model, digital surface model, and digital terrain model. DEM, DSM, DTM. DEM is basically a generic term covering DSM and DTM. So DSM or DTM is a DEM. DTM is the digital rendition of the ground, and DSM is digital rendition of the elevation. So if you subtract DSM from DTM, you get the height of the object. That is the principal theory covering 3D modeling of plants using LiDAR and photogrammetry. You compute the DSM, you compute the DTM, you subtract the both, and you get the height of the object. The first technique I'll be using is the LiDAR, stands for light detection and ranging. It basically consists of different lasers in different directions and shoots lasers in different directions and receives the reflection, and it computes the distance using time of flight technique. And the LiDAR I'm using is the BLP16 LiDAR, which is a 16-channel LiDAR. That means it consists of 16 lasers in plus or minus 15 degrees vertical field of view. And this LiDAR basically maps the whole environment in spherical coordinates, and it sends a UDP data packet. This stands for User Datagram Protocol packets. This protocol is used because you cannot use an internet protocol. This because most of those protocols check for packets, how many packets are coming and how many packets are going. So there's a delay in those things, and it's not used for real time. This LiDAR is a real time system. So if you want to use any real time system, you have to use UDP protocol because it doesn't check for any packets coming in, coming out. So there is no delay. And it sends UDP datagram protocol packets, and each packet consists of time of flight measurements, calibrated reflectivity measurements, rotation angles, and timestamps. So this is the example data packet. So you get like 754 data packets per second, and each data packet consists of, so the whole like second you get 0.3 million points per second. So it's about 0.3 million points per second. So it's also 8 megabytes per second you get. And this is the example data packet in hex format. You get the timestamp and you get distance of all like the 16 lasers. You get one data packet, you get 24 measurements from 16 lasers. As I said, it maps the environment in spherical coordinates. So if this is the LiDAR and the data point is basically a plant, and so this is a Cartesian coordinate system x, y, z, and it maps the environment in spherical coordinates. So it gives the omega, which is the elevation angle, which is fixed for a given laser in its vertical field of axis, and it rotates around this alpha, around its own axis, about 600 rpm. So for a given laser, omega is fixed, and you get the r and alpha. And from this conversion, for like a single point, you can convert the spherical coordinates into a Cartesian coordinates and map the whole system. You want to convert this into a Cartesian coordinate system because it's really easy to work in Cartesian rather than working in polar coordinates. Next thing I'll be talking about is photogrammetry. It's making spatial measurements from photographs, and main thing is you have to, so this is the camera I'll be using, a parrot sequoia, and this is a digital surface model of an image, and this is effectively a turnkey system. So you can buy the software and the camera, and you can generate 3D point cloud images. And Dr. Dorak and Felipe also already been working in the summer for collecting large image data set on alpha for photogrammetry based modeling of alpha. So we want to focus more on the LiDAR, and this is a picture showing, this is both for the LiDAR and photogrammetry. As you can see, if the leaf area index increases by a lot, then you can't really get ground points more. So you have to basically see which plant you are measuring and plan according to that. If the plant is really dense, you have to take pictures or from multiple angles, otherwise you don't get really enough ground points. If you don't get enough ground points, you can't really generate a good DTM. And the main thing is motivation behind the project. Up to now I talked about UAS, but that's not what I'm doing. So most of these like sensors are mounted on UAS, but there's a lot of uncertainty in UAS, especially due to environmental conditions. So we want to remove all the uncertainty, and so we want to build a laboratory test fixture which can remove all the uncertainty and basically move these sensors in a control and constrained manner, so that we can know how well this technology works on like field conditions. And there's also a little later on, like especially on LiDAR for 3D modeling of crops. So we want to build like a laboratory test fixture which is control and constrained, and which is also robust to environmental conditions. So that's where my object is coming. So the first object is developing the laboratory test fixture, which is control and constrained, and move this both sensors in a highly controlled manner. And the second object is validate the sensors in using known input geometries, because you don't want to go in field conditions without validating the sensors in laboratory conditions. So we want to validate these sensors in using known input geometries, and after that we will be modeling. We will go to field and model the physical structure of alpha and correlate it with field measure parameters. So next thing I'll be talking is optically one, which is the development of laboratory test fixture, which is linear motion system. I'll be talking about how we developed it and the motion control system went into it and the validation of the system. So some design constraints regarding the linear motion system. So it needs to be at least less than 1.8 in, these are 1.8 by 1.8 by 3.6. And because we need to fit the whole system inside the trailer, inside Dr. Sama's trailer, and it should be easy to carry, it should be lightweight, and it should also be robust to external disturbances. And it should be corrosion resistant, because I never went to alpha, but Felipe said that there's a lot of water there, there's the water up to here, so you want to be corrosion resistant as much as possible. So we based the whole design on 80-20 aluminum, it's anodized aluminum, so it's corrosion resistant, And we base the design on this thing because it's easy to assemble into a rigid structure without welding or any permanent parts. You see, these extrusions are used to we can assemble and disassemble really easily. I assembled like 10 times up to now because we kept adding things, so we assemble and disassemble the whole thing like 10 times, so it's really easy to assemble and disassemble. And this is the torque requirement of the system from mass 3 kilograms A and R, which the mass comes from the carriage assembly, which I will be showing in the next slide. So this is the whole linear motion system design. So the mass comes from this thing which moves back and forth. So the mass of this is 3 kilograms. So we made the maximum acceleration to 5 meters per second square, and the R comes from this stepper motor, which is 0.0273 meters. So it comes out to be 0.41 Newton meters, the torque requirements. And some of the design constraints. So the whole thing is bigger than the specified measurements, but you can take the whole thing off. So there's like a sliding joint, so we can just take the whole thing off, and each one of them is less than the prescribed measurements. And so this is the top assembly and the frame assembly. So one thing I didn't talk about is LiDAR has a range of 1 to 100 meters, so 1 meter to 100 meters. So you cannot see some things which is really less than 1 meter. So we want to build a frame which can sit on the top. So the distance from here to here is 2.1 meters. I think the biggest alpha that can grow, the tallest is about 1 meter. So we can at least get 1 meter height, so it can model accurately. And this is frame, and this is the motion control system which will run the whole system. And these are 2 limit switches on either side so that it protects from going away. And yeah. So these are the sub-assemblies. This is all we designed, and these are the wheels. I said one of the design constraints is again easy to carry. It's really easy to carry because we have wheels. We don't have to lift anything up. We can just push it around. And this is the sliding joint I talked about. And one of the design constraints is again using it should be robust to environmental conditions, which means so we use these braces so that used a lot of braces so that even if you push around, it just dampens the whole vibrations. And this is the motion control system which drives the whole system. So this is the stepper motor we bought from the torque requirements. It turns out to be 3 Newton meter torque, which is 7 times what we got from the torque requirements. So this is the other way around. So we bought the stepper motor, and it turns out to be safety factor of 7, but it's okay because even if you want to like run at higher accelerations, it's good to have because it doesn't add much weight to the system. And this is the timing belt pulley. That's where the R comes from. And this is the limit switch, which again I told you, I think it stops the carriage assembly from going out. Otherwise, if we give like different distance or more distance, it will just shoot out and it will just destroy the whole system. And this is the main motion control system which is driving the whole. So that's a 70 volt DC power supply, which is the main responsible for stepper motor, and it goes down to the regeneration clamp. So the regeneration clamp is basically used. So if the stepper motor decelerates at really high rate, there's an inductance in stepper motor which generates a really big back EMF. So sometimes it will be greater than the voltage sometimes. So then it can destroy the whole thing. So the regeneration clamp basically clamps the whole, like it destroys the back EMF from destroying the whole thing. And the power goes from the regeneration clamp into the stepper motor controller, which drives the stepper motor. The computer sends serial commands into the stepper motor, which gives the appropriate pulse train for the stepper motor to go in the desired velocity profiles. And we have different power supplies, 5, 12 and 24. They're used to power LiDAR and any other things we want to add in the future. This is the user control interface, so we can just select different velocity profiles, different accelerations, velocity, deceleration, and total displacement. And by selecting these, we can, if you click run, it will send the appropriate serial commands to the stepper motor controller, which sends the corresponding pulse train so that it can run the stepper motor in a desired velocity profile. This is the example velocity profile. So it accelerates to a steady state velocity and decelerates to rest, and it again comes back in the same velocity profile. This is about like 1 meter per second steady state velocity. So not only want to build a system, we also want to validate the system. So we validate the system using a robotic total station or total station symbol. And this is the main picture where you can see the total station and the rectangular prism. So what it does is it locks into the rectangular prism, and whenever it moves, it tracks the rectangular prism. So that we fix the rectangular prism to the carriage assembly, and we check for the distance and velocity. So if it's moving accurately or if it's going the right distance. And we got the data just yesterday, so I didn't really process it. But I looked at some of the data for the distance, and the error varied from 2 to 4 millimeters. So I think it should be perfectly fine. Next thing I'll be talking is the Objective 2, which is the validation of the system using known input geometries. I'll be talking about data logging and data post-processing. Also I'll be talking about validation using known input geometries. So the LiDAR data logging, so you see the user control interface. So there is a run command. So if you click the run command, it not only sends the serial commands to the stepper motor, it also connects to the UDP port, which can start the LiDAR data logging. So you want to synchronize the measurements with the start of the linear motion system. So that's what we are doing. So at the same time you're starting the system, you're also starting the data logging, and you're collecting and simultaneously collecting the data coming from the LiDAR with the velocity measurements. And the stepper motor controller gives the appropriate pulse time to run the stepper motor in desired velocity profile. This last one is you get the raw data with the velocity values, and after that is the data post-processing, which is, so you get the raw data which is in Unicode format, I think, and after that you put it in a Python script which converts into a hex file, like the one you see hex format, and in an Excel file, and after that you read the values in a MATLAB and convert it to a decimal format, and you get the timestamp, azimuth and elevation angles. After that you convert the spherical coordinates into Cartesian coordinates to get the XYZ values, and using velocity project these XYZ coordinates into a 3D point cloud, and after that you generate DSM and DTM using the 3D point cloud using algorithms. As I said, before going to the field, we want to validate the system using known input geometries. So something like this or a rectangular block will be really useful to validate the system. And as a courtesy of the lab, found these two. So we also want to accurately scan these two, so we can find out how accurately scan this. Because these are more like basic and these are more complex, so we want to scan these things and see how accurately it can scan these two compared to those two. The last one I'll be talking about is Objective 3, which is modeling the alpha in field and validating the field data conditions, field measured data. And after you get the DSM from DTM from the data post-processing, you remove some outliers and you basically apply a threshold and separate the ground points from the plant related points. And so this is, and you divide the resulting DSM and DTM into numerous identical blocks. So this is basically taken from a paper which is similar, but they didn't include any disturbances. So they basically put this thing on a tractor and run at 3 to 5 meters per second, and they didn't account for any disturbances. But this is what you get similar to it. So you divide this into numerous blocks of DSM and DTM and measure each plant height. You can measure each plant physical parameters from the XYZ coordinates you obtained before. And this is my project timeline. I work right here right now, and most of the first activity is almost done, and I did the data logging and data post-processing, and I still have to validate the system using known input geometries. And after that, the third activity will be modeling alpha-alpha, which I'll be doing probably next 2 weeks. And alpha-alpha is almost being harvested, so I'll probably have to collect some data in next spring, in April. And I'll be publishing a paper from the Objective 1 and Objective 2, and want to defend my thesis by August 2018. And last, I want to thank Dr. Sama for constant support and guidance for the project, and Felipe for initial design, Lee and Ed for fabrication, helping with the fabrication, and Chris for working with the LiDAR, and Ali for assembling hundreds of times. And yeah.
So you just casually said you get all this data and you're going to determine the outliers and throw them out. How do you do that?
As of now, I'm not sure right now, but so Dr. Dvorak got like a text fixture which is 1 meter by 1 meter, I suppose. So we will remove the data which is more than 1 meter. Like, so if it's more than 1 meter from the LiDAR, it will be removed. Like if it has a coordinate of y which is more than 1 meter, it will be removed like that. So we will remove all like those points from the data, checking its y or x or z coordinate.
So basically screening out everything that isn't like right
Exactly.
in
Yeah.
that.
Are you going to put some bigger wheels on it when you go into the field? I saw it probably works great for the lab. I was wondering if you go in the field.
We don't want to put the wheels in the field. They have like studs, so we want to fix the whole system using the studs instead of fixing by the wheels. Because it's probably too damp.
So does that mean you're going to anchor it
Yeah.
on a given spot?
Yeah. It does also get like, so it's wheel and it also has like studs, so you can. So it has both, so we want to fix it using studs instead of wheels in the field. Yeah.
How concerned are you with how level the fixture is while you're out there? Do you have a way to adjust for that, or does it matter because you have a way to like tell, or do you like make level up before you start, or does it even matter? I guess is the question.
I don't think it does matter because only thing you see is x, y, z coordinates. I think once we get them, it really doesn't matter. But that's a good question.
I think as long as you measure the surface.
Yeah, measure the surface.
What other questions?
So I guess, what do you worry about the most, like pitch roll or yaw or wind, with like, I guess going from that to a UAV, as far as like your LiDAR accuracy?
Mostly the wind, and I mean, several different things. I mean, wind is one of the conditions, and I would say the speed is one of the conditions, because I mean you can measure speed with UAV, but it's not really that accurate compared to this thing. And it can affect. I mean, it doesn't affect a lot, but we want to remove all those things, and we want to determine how well it works.